So your binary relations homework is due this weekend. You should be working on it. I haven't seen a lot of Piazza posts. I imagine you're just not working on it yet, so you should start it soon. In case your TAs just aren't around on Sunday when you're trying to ask all your questions. But your peer tutor friends will be around, so hopefully they'll answer them. Okay, so we're going to start on counting, and the reason why I kind of wanted to rush through binary relations and get to counting is because that was the subject that people did the worst on by the end of the course last semester. So although induction is hard and you guys had some trouble with that, counting was the thing that it was hardest. And the reason for that is that counting problems are, well, it's not just counting from 1 to 10. So when I'm counting things, what we're trying to do is translate English, a description of like all the possible things I might see. I actually want to count how many things those are. But it's extremely hard to count things because there's lots of overlap. And if we don't take that into account, we will always count too many things. So that's what counting is about. It's actually about figuring out how many different things might I see in different situations, or how many different ways something might happen. Why would you want to know that? Probabilities. So that's the main reason. So the main reason you want to count things is to know how frequently things show up, or also to know like whether I've covered all the cases in a program, how many rows in a truth table I might need, that sort of stuff. So counting things is really important for a computer scientist because we need to be able to know how to construct our tests, how many different things we might need, how much storage we might need in a database, that sort of stuff. So very, very basic thing that computer scientists have to be able to do. And it's quite challenging because it goes immediately from a couple of easy definitions to problem you have no idea how to solve. So we'll get started. All right, so the first thing that we want to do is talk about some basic things. So we've already talked about a few things. So one thing we've done, for example, is we have defined the Cartesian product of two sets, right? And so if I have a set A and a set B, then I can define their cross product, and we know that the size of that is what? So how many points do I have in A cross B? So if I have 2 points in A and 3 points in B, then if I make a new cross product, I have 6 things, right? So it's going to be the size of A and the size of B, and we're going to do something with them. What are we going to do with them? We're going to multiply them. This is called the product rule. So that's an actual cross. It's not a times. So when I take the cross product of two sets, I actually multiply the sizes of the sets. And you could use this rule recursively or inductively to actually show that if you do any number of them, you still do the same thing. So how could I prove that the 2-set rule implies the 3-set rule? There's a very simple thing I can do. Draw some parentheses. So cross A cross B with C. So I just draw parentheses around A cross B so I could get A cross B cross with C. And using the first rule above, that's going to say give me the size of A cross B and multiply it times the size of C. And then I can just now apply the rule again to get that A cross B is the size of A. The size of A cross B is the size of A times the size of B, and then we copy down the times the size of C. So this is one of those easy rules. So what this corresponds to is, it's easy for sets to see how it corresponds to, but it also corresponds to me saying you can have 2 different sides with your meal. How many possible ways are there to order a plate? So, any of you go to Waffle House? Okay, one person admits to Waffle House. I like Waffle House. They count like how many combinations of ways you can have your hash browns. It's a lot of ways. Because you can have all these different options, right? So counting these actually gets pretty large pretty fast, because you can see when I have ands, so product rule means if I have an and. So if I have a situation where I have two things and they're both occurring at the same time, then that's an and condition. So if I say I'm going to make up a committee of people and I need to have one person from math and one person from computer science, then all the different ways of choosing a person from math and all the different ways of choosing a person from computer science will be multiplied together, because that's an and condition. So we use the product rule when we have an and condition. And so we started out the class talking about and conditions, so we really know when those apply. Okay, so the next thing we need to do is talk about when we have an or condition. And that is called a union rule. So, if I have a union of two sets, and I want to figure out how big the resulting set is, we've done this too. We looked at it, we said, okay, well, we take the first set, and then we add the number of items in the second set, but there's a problem with that, right? Because inside this set, there's also some stuff from A intersect B, and it's also in there. So everything in this A intersect B set got counted exactly 2 times. So I have to subtract off each one of those once. So this is called the union rule. So if I take the union of two sets, then I have to add together the amount of things in the first set, the amount of things in the second set, and subtract the intersection. If I do this for a larger set, say for 3 things, let's figure out how that works. So again, this magic rule of using some parentheses will allow us to extend a rule for 2 things into a rule for 3, and you could actually repeat the process to go to however many things you take the union of. Then we can get that the size of the union of 3 things is the size of the union of A union B plus the size of C minus the size of A union B intersect C. Okay, good. So we know how to use our 2-set rule for that one, so we can get that that is the size of A plus the size of B minus the size of the intersection of A and B. Then we copy over the plus the size of C. And now this is funky. We don't know what to do with that, right? We only have a rule for unions. Is there a way for me to change this intersection into a union? Yes, there is. We can use our old logic distribution rule, because unions and intersections are just like ors and ands. So we can change it and actually say that this is actually on the inside going to be the same as A intersect C union B intersect C. So the way you do that is you take the first one and the operator in the C, put them together. Then you take the second one, intersect C, put those together, and then you use the union operator right there. So now we've turned that into a union, and we can use the 2-set union rule to tell me how big that is. So let's just call that X. So this is going to be X, and then we're going to subtract all the stuff that this is equal to. So it's going to be the size of A intersect C plus the size of B intersect C, and then we have to subtract the intersection of A intersect C intersected with B intersect C. So all of that was the size of our A intersect C union with B intersect C. Now, does anybody see a way we can simplify this? The last term? We can drop one of the C's, because C intersected with C is the same. And if I have all intersections, I can rearrange everything. That's called the commutative rule, right? And there's an associative rule that also works, so I can just rearrange and put parentheses any way I want, since all the operators are the same. So this is actually going to be A intersect B intersect C. And there's a minus out here, so I'm going to change that into a plus, and this into a minus, and that into a minus. So if we rewrite this entire thing, so I put back x, I get the size of A plus the size of B, and I'm going to go ahead and write the size of C here. I'm just rearranging, so I've just got these three terms. Now I'm going to subtract the intersections. Of two things, and then I'm going to add the intersection of 3. So we've just arrived from the 2-set rule, union rule, to a 3-set union rule. And you can extend this to n sets by adding the odd sizes of intersections and subtracting the evens. So if I had 4 things, A union B union C union D, then I would be plus the size of A, size of B, size of C, size of D, subtract all the doubles, add all the triples, subtract all the quadruples. Intersections. Now this is useful because it's usually pretty easy to figure out what's in an intersection. So, like, if I tell you, here's a person who has blonde hair and blue eyes, like, it's easy to count the people who have that. But if all I start out with is the information about blonde people and information about blue-eyed people, and I don't have the information about both, it's actually hard to figure out what those numbers are. So intersections are a little bit easier to work with, and that's why we changed unions into intersections for counting purposes. Also, these things are well defined, so I know which subsets things are in when I get into intersections. So remember from our Venn diagrams that we did when we did set theory, that when we start looking at multiple sets, it gets more and more complex, like how many overlaps they have. So the way this works is, when we count the singles, that's like counting these circles, right? And then when we subtract the doubles, that's subtracting these footballs, right? And then when we add back in the triple, that's this triangle in the middle. So when we add them, each of those footballs got added twice because of the doubles. But then if we take all the footballs out, then this middle one's been taken out every single time. So that's why we have to add it back in. That's why it works that way. Okay, so these are the simple rules that make it look like counting is going to be a piece of cake. So the reason why it's not a piece of cake is sort of the similar reason why predicate calculus is not a piece of cake. Because then we start speaking English. And then you're like, well, I don't know how to translate the English into these nice sets. Okay? So let's start out with a problem. Okay, so first I'm going to start out with this problem. How many different license plates are there? So then I'm going to put another word in there. And I have underspecified this on purpose because I want you to figure out what we need to know in order to answer this question. What do we need to know, Stephen? Timothy? I'm sorry. We need to know what characters we need to use. So those are two great things we need to know. So do we mean license plates that are issued or all the possible ones? We want to answer this one because issued is a data entry problem and we don't care about those. Yes? That's right. How many characters are on a single license plate? Okay, so if we answer those questions, if I say, okay, we can use letters and numbers. And then I say we have 7 characters on there. Can you answer the question? Yes. So I would like you to try to answer it, and then we will check our answers. Lovely. I did not expect that answer. All right. Good answer. So if you can have up to 7 characters, this is the answer, assuming that you can't have 0 characters, right? If you had 0, that would be still also okay. You would just add a k equals 0 to the bottom. So this is the answer if you can have less than 7. What if you can have exactly 7? 36 to the 7th. And what's this answer? So this answer means the person figured out that the product rule applied and used it on a couple of numbers. It's going to happen to you. You will be on a problem and you'll do a rule and it will be the wrong way. So don't laugh. It happens to all of us. It's just going to happen to you at a different level if it didn't happen to you yet. So that's what counting problems do. We got it out of the way with early. By the way, when I took this class, which I did take here with Dr. Bitzer, and not going to tell you what year. It was like last year or something. Counting was the hardest subject for me. So you can have aced everything up to now, which is what happened to me, and then pew. Okay, so the reason is that you have to practice. You have to do a lot of these problems, and that means you need to get your book out, and you need to work every single counting problem you can get your hands on. Okay, let's go back to this picture of the Venn diagram. So I pointed out, when we talked about the inclusion-exclusion principle, that's what it is when we extend the union rule into more than 2 sets. It's called the inclusion-exclusion principle. And I wanted to draw a picture for you to help show you why it ends up the way it does. So if we add all the elements in A and all the elements in B and all the elements in C, we have these footballs that got counted twice each, right? So A intersect B got counted when you put A in. It also got counted when you put B in. A intersect C got counted when you put A in and also when you put C in. And then B intersect C got counted when you put B in and when you put C in. So if you take those footballs out, the poor diamond in the middle, the poor triangle in the middle, got taken out 3 times. So now we have to put it back in. So this is why the inclusion and exclusion principle works. Is because when we start trying to solve the problem, we introduce a new one, then we solve that one, we introduce a new one, and then we solve that one. So however many sets we have, we introduce that many problems and solve all of them. So that's why we have to do the inclusion and exclusion principle. Any questions on that, or did you want to see it longer? See it longer? What you should do when you're looking at these pictures is you should think about that these circles are actually like fences that are corralling like cows or some other kind of marbles or something in there, and that they're just that there's actually things in here that you're counting, because that's what you're doing. So that there's points in here, and they're all getting counted according to where they are. Okay, are we ready? Are we done absorbing? Yes? Okay. All right. All right, the next thing we need to do, so we introduced one thing when we were solving our last problem on license plates. License plates are like a classic counting problem. Everybody does them. So what if I told you that the first two characters have to be, or let's say the first three characters have to be letters, and then the last four have to be digits? Now how many possible license plates, possible different license plates do we have? So try to work that out, and then we'll talk about it. So the question is there order? So I put this question on here, but I didn't talk about it because everyone gave me an answer that assumed that order does matter on the license plate. Does it matter on the license plate? Yes, it does. So if the letters or numbers are in different orders, then they're different license plates. So I can have ABC 1, 2, 3, 4 and BCA 1, 2, 3, 4, and those are different license plates. So order does matter. It matters what letters and numbers are in what order. So we're going to assume that on these new license plates, it still matters what order they are in. Okay, so if we have three letters, I was using some letters from some other language. It's 26. If we have three letters, 26 cubed, four numbers, four digits, 10 to the fourth. And we say digits instead of numbers to be clear that it's only one digit, not actually four numbers like 10 and 12 and whatever, because that would be different. Do we add or multiply? Okay. Anybody find that confusing at all? You do? Okay. Thanks for answering honestly. So it's confusing, but if you think about it, I want to ask the question. If the question was that you had either letters or digits, it would be plus. But if I say you have three letters and you have four numbers, then it has to be times because that's the product rule because we have an and. So sometimes you can't hear the and explicitly in the problem, so you have to think about it. Is it the case that I can have one or the other, or is it the case that I must have both? If it's both, it's times. So that is a good question. Okay, so it is times. So one of the reasons why counting is hard is because a lot of times some of the problems seem really easy at first, and you just write, oh, something raised to something power, and I multiply those, and it's easy. Okay? But make sure, the big important thing is to make sure that you have specified the problem and you understand the problem. That's really the hardest thing with counting, is that you understand everything. You make sure you answer all the questions you need to answer before you start counting. So let's look at another problem. Okay, so recently there was a NPR program about runners from Kenya. Did anybody hear that? You guys know that there's a specific tribe in Kenya that kicks butt at Olympic racing, right? So they were talking about on there that maybe it was just physique and that they have this special body type and that was the reason why they could run. And then they start listing it, but then it turns out that all of Kenya has all the same things. Like everybody has to run everywhere, and they have similar physique, and they have similar background. So it can't just be that, because there's one tribe that does better. And then they started talking about what it was. There was a guy that lived there, and he said they have to go through these horrible initiation ceremonies, and during the ceremony, they're not allowed to make a sound. And I'm not going to tell you what the ceremony is, because I don't want anybody to cry. But they're not supposed to make any sounds, and they start when they're little, hurting themselves and practicing being stoic. And they talk about that's actually what you need to do if you're going to run in the Olympics, because it hurts to run, and you have to get past it so you can go faster, instead of slowing down and going, oh, this sucks, which is what most of us do because we are Americans. Okay, now I told you that story because sometimes when I'm talking about races, I might actually like races, not races of people. I'm talking about races that we run. Okay, I actually sometimes want to know what's the nationality of the winners, and I might not care what order the race was. I just want to know, did people from Kenya make it in the top 3 or not? So some question that we have, like what you guys asked before, is does order matter? So that's always a question when we are counting something. So if we have a question like, so runners run a race. So let's see, how many do we have? Let's say how many are usually in the Olympics? Like 100 or, I don't know how many people. I haven't watched this stuff in a long time. They end up really having like 10 on the track at the same time, right? Maybe 7 or 10 people. Okay, so let's just say it's 7. Okay, so we're going to have 7 runners running a race. And how many ways are there for the runners to finish? So the counting problem is not for you to write down a formula. The counting problem is for you to decide or determine what is the problem. Have I given you enough information? No. Do I care about the order? Do I care about the order? Yes, it's a race. I'm asking about the order of the finish. How many places do I have? Okay. Pretend you're an Olympic runner and you go to the Olympics. Are there 7 places? No. There are 3. So it matters how many places you're going to count, right? So you need to ask the question, how many places do we care about? So we can say 7 to start with, and then we're going to solve the 3 problem. So the other thing I like to do is I like to draw a picture that I can use to describe what the different orderings look like. Okay? And my favorite way to draw a picture is to draw some blanks that represent where I can put things. So if I care about all 7 places, I'm going to draw a blank for each of the 7 places. 6, 7. Now, the first thing I can tell from this problem is I know that all 7 runners are going to place, and that's an AND condition. So I automatically know that whatever's in the blanks, I'm going to multiply them. So I figured out that I'm going to use the product rule. Now, the first thing I do is I say, how many ways are there to choose the first place runner? There are 7. How many ways are there to choose the second place runner? 7, except not after you chose the first place one, there are 6, because you can't be in both first and second place at the same time. How many third place? 5. Fourth? There are 4, 3, 2, 1. That's equal to 7 factorial. So why does this look so different than the answer to the license plate problem? Why is it a factorial and not a power? We care about the order for license plates also, right? We cared about the order of the letters and the numbers. No person can be both first and last, but on the license plate I can have the first and last things be the same, right? There's no replacement. So this is the most confusing thing in counting, is replacement. So here we have no replacement. And this is one thing that I found the most confusing also, is what the heck is this replacement thing? Because I'm not replacing any people, right? So it doesn't even sound like it has anything to do with what I'm trying to do. But it's a word from the kind of counting things where you're thinking about like putting things in a hat and then pulling them out. And then replacement is whether you put it back in the hat or not. But we don't pull people out of hats. But you still have to think about replacement. So you have to ask yourself the question, when I'm counting these items, can the same item appear more than once? And if it can, then we we don't have replacement. Sorry, we do have replacement. We replace that value in the sort of pool of possible values. If they can't repeat, if it can't be replaced, like once I use it, I can't use it again, then we don't stick it back in the pool, and that means that these numbers decrease every single time. Yes? That's a great question. So let's answer that question. Okay, so the question was, what if we know that something can repeat once but not again? We can't use fancy formulas for that. We have to, again, figure out what the problem is and then figure out how to count it. Once we're really sure that we know what the problem is and we can draw a picture and we understand how to list out all the possible different solutions. So, how many bit strings are there with exactly 2 ones? What other questions do we need to know? How long is the string? Let's say it's 10 bits. Does order matter? How do you know? Not because I just wrote the word yes. Order matters because the definition of the word string includes ordering. So when I see the word string, I assume that there's a beginning and an end of the string and that things in between are strung on the string in an order. That's where it came from. So the word string is like our computer science adoption of an actual string. Like this. There's a beginning and an end, and if I put stuff on it, I can't take things out and rearrange them really easily. Okay? So a string implies order. So if you see something like race or string or anything that normally has order, you can write down, I assume that order matters. And you should write that down because if you make a different assumption than we meant when we write the problem, we can give you partial credit for solving it based on your own assumptions. Okay, so we know how long the string is. We know whether order matters. Now we need to draw a good picture. So we have 10 places, so that's one thing we should do, is draw our 10 places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is a tricky problem because the solution does not involve putting times in between these things. What it involves is actually numbering these positions. So this problem, does it have replacement or does it not? Yes, because every position can have 2 values, right? And there has to be replacement because I'm using ones more than once and I'm using zeros more than once. So there is replacement. We do have replacement. So the only good way to count this is to pick out which places I'm going to put ones in. So out of these 10, I'm going to throw those 10 in a hat and I'm going to pull out 2 numbers that are going to tell me where to put the ones. And then everything else is going to be zeros. Okay? So this is a whole different kind of problem. Once I transform the problem into picking from the 10, does it matter what order I pull the numbers out of the hat? No. So now I've just transformed this problem into an order doesn't matter problem. So here's the tricky thing. It did matter, and we had replacement. But now we're going to make it into order doesn't matter, and there's going to be no replacement. Why would we possibly want to do that? We want to do that because replacement is irritating and it will mess you up. Now, I'm not going to make you do it in class because it will take forever. But if you would like to torture yourself with why we are actually doing this, you can actually try to figure out a way to put a 1 in and then figure out how to do all the other ones and try to do like a branching decision tree, like how I could put the 1s in and figure it out. But I'm telling you, this is the very best way to solve this kind of problem, is to transform it into a problem that doesn't have replacement and doesn't have an order. Now, here's the problem, though. Solving problems without order, we don't know how to do. So then we have to transform it again into a problem where order does matter. So does anybody know actually the formula for this? So if I put those 10 numbers in a hat and I pull 2 out, how many ways to do that? Has anybody heard of a formula for that? It's 10 choose 2. You've heard of 10 choose 2? So it's going to be C 10 choose 2. That's actually the answer. So what we're going to do now is tell you what that is. So I'm going to make a pool of 10 things, and I'm going to pick 2 out of them. And I don't care what order I do it in. So the way we do this is we're going to pick 2, so we're going to make 2 blanks. And these are ordered. Like anytime I make blanks, they're ordered. It's just like a string. If I put 2 blanks next to each other, I'm implying that it matters which order I do things. Okay, so now we are doing an ordered problem. When I pull out the first number, how many possible choices are there? There are 10. When I pull out the second number, how many choices are there? There are none, because I don't want to pull the same out, because I need 2 places to put 1s in, and exactly 2. So I don't throw that first number back in, so I have 9 choices. Do I multiply them or do I add them? I multiply them because I do them both. Now, this was with order mattered. So what if I pulled out 10 first, and then I pulled out 9? That's the same as pulling out 9 and then 10, right? But I don't actually care about that. So what I want to do is, for all the possible ways I've pulled out stuff, I want to divide by the number of ways that they could be rearranged. So for every pair that I pull out, so for every AD pair, if I count it this way, I've also counted BA, right? Does that make sense? So that means for every possible thing that I've counted here, I've actually counted everything I care about. I've counted it twice. So I'm going to divide this by 2, because that's how many times each of my unordered things got counted. So now let's figure out what this formula actually means. So this looks a whole lot like our picture for our race ordering, right? So for the order of our race, we actually had this multiplication of numbers that were decreasing. And so this looks like the start of that, and it is. So the formula for 10 choose 2 is actually 10 factorial divided by 8 factorial 2 factorial. The reason for that is we say, well, let's do the 10 problem. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. But we actually are going to stop after we pick 2 of them. So I'm going to take 10 factorial and divide it by the number after that slash. So I'm going to divide it by 8 factorial. So that's what this part is to get that 10 times 9 we had before. And the reason why I do that is because we might choose different numbers of things. If I chose 5 things, then I would have had 10 times 9 times 8 times 7 times 6. So however many things I pick, I want to go to the next number and divide by that factorial. And then we divide by the 2 factorial because that's all the ways to rearrange the ones we did pick. So whatever number this is, so this number right here is going to be n. That's the size of the set that I'm choosing from. And k is the number of items that I'm going to choose. And so my formula is going to be n factorial over n minus k factorial times k factorial. So we figure out things where order doesn't matter by counting things where order does matter and then dividing by the different ways to rearrange the things that we counted. So this is a formula for what we call, these are called combinations. And this formula is for no order, so no ordering, and without replacement. And if you have a fancy calculator, this is what they have on them. So if you have something that says NCR on your calculator, that's what it's for. The reason why I'm using the letter K is the same reason why I put K instead of I in all the summations and stuff. Because N's and R's when you're fast on the test look the same. And they look the same when I'm writing fast up here. So then you're like, which one is which? So K's and N's don't look similar. So that's why we're using those. Any questions about this so far? So let's go back to our bit string problem and see how that helps us. So when I drew my picture, what I like to do now is actually draw myself an example of picking out those 2 ones and make sure it makes sense. Okay, so I'm just going to pretend I picked 3 and 7, and then I'm going to put zeros everywhere else. Once I pick those 2, so that was C10-2 was the number of ways I could pick those 2. I have no choices about where to put the zeros, right? Because they go in all the other places. So all I get to do is pick out where the ones go, and I have to put zeros everywhere else. So if you read a regular probability or statistics book about this, they will just tell you that the formula for combinations with replacement is some C formula with some N's and K's added together. I think that's confusing. So what I do is I like to call this a divider problem because we're dividing our 10 things into things that have zeros and things that have ones, right? Which ones we're doing. So this is a problem with replacement and order matters. We're transforming it into an order doesn't matter problem, and we do it by seeing how many things do we need to pick and from where. Okay, so we've seen a few different formulas so far. We've got the product rule and the union rule. The first problem we did with the license plates where we were allowed to reuse the letters and numbers, and we had 7 of them. That's a permutation with replacement. So permutation means order matters. So the word permute means change the order of. So you can remember that permutations means something where the order matters. So permutations with replacement. So this union rule was So what's the formula if I have n items to choose from and I choose k of them? This is a permutation where order matters. So it's just like the initial license plate problem you guys had, where you found that the answer was 36 to the 7th. So it is what? N to the k. So permutations without replacement, that was like our race problem. If I just order all n items and none of them can repeat, well, that's what I get. But if we go back to our race and we don't care if we don't win in the top 3, then we really want to stop that permutation counting before we get down to 1, right? So let's go back to that race problem and let's see how many, so we have 7 runners and we only care about 3 places. So now we want to figure out the orders of finish. So I draw my 3 places. There's 7 people who could win, 6 people who could be in second, and 5 people who could be in third. So that's going to be my answer for how many ways there are to have finishes in the race if all I care about is the first 3 places. But what is that equal to? That's equal to 7 factorial divided by 4 factorial. So this was sort of an imaginary thing. Was when we start a factorial, we can finish it, but just by multiplying by the rest of the numbers. If we divide those out, that's telling me what the formula is for where I have n items to choose from, and I'm ordering k of them. So this is our formula, is going to be n factorial over n minus k factorial if we have k, if we're only choosing k items. Choosing to order k of the n items. Now, the bit string problem is not like a canonical problem. That was a problem we had to read and figure out how to do. But that trick of when I figure out that there's replacement going on, you need to map it into a different problem because replacement problems are a pain. So what problem did we map it into? So if we actually look back carefully at the bit string problem and we think about what items are we choosing from to make the bit string, we're choosing from 2, right? Because the set we're choosing from is 0, 1 to make a bit string. So if the number of items we're choosing from so that's normally called n in our counting problems. The number of items we are choosing, that's how many blanks we would draw. That's 10 because we had a bit string of length 10, and that's usually k. And we said that we had exactly 2 1s, and the remaining are going to be 0s. This is where I stop using formulas for problems. Okay, so then I'd go, I don't care what this n and k are. So I draw my 10 blanks, and I think about, okay, how do I figure out where those 1s go? And if it doesn't matter which order they're in, then I just say, okay, let's put the 10 numbers in a hat and pull out the 2 where we're going to put the 1s. Or just throw darts at them and figure out which 2 I'm going to do. So in reality, what we turn this into is we transform the problem. So now we choose from 10 positions, we choose 2 of them, and order doesn't matter. So then now we know that. That's going to be n is 10 and k is 2. So we have C 10, 2 would be the answer for there. So when we have a problem where we're going to choose from n items and we're choosing k of them and order doesn't matter, we have this formula for C and k. So let's go back to writing formulas. So where we have combinations, this is where order doesn't matter. That's what we call it when order doesn't matter. We have n items to choose from, and we choose k, and there's no replacement. Then ordering those n items is what we do first. Then we divide by n minus k factorial because we only are choosing k of them. That's how we get those first few terms of the factorial. And then we divide by k factorial. So this is the number of ways to rearrange something that we choose. So remember that this part was the ordering of everything. The reason why I'm telling you this is because I don't want you to try to do counting by memorizing the formulas. I want you to really think about the problem and think about how do you draw the items in the solution. What do they look like? If I drew all of them out, what do they look like? So before I told you how to do the bit string problem, I would actually start listing out all the possible bit strings, and I'd also solve it for a smaller n because a length 10 bit string is a pain. So let's actually go do that problem right quick, because I don't want you to think that I'm telling you to do one thing that I don't do. So what I actually do when I'm doing a counting problem is I try to write down all the different solutions. And if it's a tractable problem, one I can do in less than an hour, I'll do it. So let's just multiply out, by the way, 10 choose 2. So that is 10 times 9 over 2, which is 5 times 9, is 45 things. I'm not going to do those, okay? But we'll do 5. So we'll do a bit string of length 5, and they have exactly 2 ones. Okay, that's all the ways that they can stay stuck together, right? That's all the ways they can have a 101 pattern. That's all the ways they can be 2 apart. That's all the ways they can be 3 apart. I think that should be all of them. So let's figure out how many it should be. We have 5 positions. We're going to choose 2 of them. So it should be 5 times 4 over 2, which is 5 times 2, which is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Amazing. Okay, you should always check your answers. You should do this and then check and see that your list has everything. So you should do this. For every single counting problem, you should try to write down all the different orderings. Yes? That's a great question. How do we get the 3 factorial and the 2 factorial? So the 5 factorial started out because I have 5 things, 5 blanks I'm going to choose to put ones in. And I'm going to number them, and I'm throwing them in a hat. I'm going to throw darts at them or pick them out of a hat. Which 2 are going to have bit strings in them? So I'm going to choose 2 of them. So these are actually now items I'm choosing from. So they're in a pool. So I actually am choosing to put 2 blanks in. I'm just going to write down the positions of where the ones go. So for example, this one, I chose position number 1 and position number 2. Right? To put the ones in. And this one I chose 2 and 3 to put the ones in. And this one is 3 and 4. And this is 4 and 5. And this is 1 and 5. So these ones are actually all the different ways of choosing 2 numbers out of 5. So it's the same as all the number of pairs out of 5 numbers. So this is going to be 1 and 3 right here. That's 2 and 4 right there. 3 and 5. 1 and 4. 2 and 5. So there were 5 choices to begin with when I started pulling numbers out of the hat. So here's my hat. Okay, I'm going to choose out of the hat. There were 5 choices to begin with. Once I chose 1, there were 4 left. So I always use factorials because it's easier to do that than it is to say, multiply all the numbers where you start with 5 and go down to whatever the last one you did is. Okay, it's much easier to say, well, just do a factorial, but then divide it by another factorial so you can get rid of all those terms you don't want. So this is the same as the rest of the factorial here. So if I just take that and divide by that, that's what the 5 factorial over 3 factorial is. So that's just multiplying 5 times 4 by 1. But now I can use a cool formula. So this is now equal to 5 factorial over 3 factorial. The only problem is now that when I did these choices, the way I counted them, when I said there were 5 choices to pull out, that involves I could choose 1 first and then I could choose 2, but I also could choose 2 first and then choose 1. So those 2 different things are counted twice, but I only want to count them once because I don't care what order you pull them out. So this 1, 2 got counted twice. This 2, 3 got counted twice. 3, 4 got counted twice. 4, 5 got counted twice. 1, 5 got counted twice, and so on. So I want to divide by 2. And it's not just 2. It's dividing by all the different ways to arrange everything you chose. So whatever k is, if I chose 5 of them, there would be 5 factorial different ways of listing 5 items that I chose out. But I only chose 2, so I'm only dividing by 2 factorial. That's where it comes from all the different ways of ordering the thing after I take it out. The 3 factorial was because the answer I wanted was 5 times 4. But there's no good way to write a formula for that. So what I do is I say, well, that looks like the beginning of a factorial, which just happens to be this. And so I can get these 2 numbers if I divide by those. In fact, it's the same as multiplying by 1, but now I get to use n factorial for the top, 5 factorial for the top, and 3 factorial for the bottom. Does that make sense now? So it's a math trick. That's why we divide by 3 factorials, because we didn't actually want 5 factorial to begin with. We wanted 5 times 4. But then we want to do a general problem. I might be doing like 10 choose 5, and that means I would need 10 times 9 times 8 times 7 times 6. But that's the same as 10 factorial, but take out 5 factorial. So it's a math trick. But we always want to learn from the tricks that other people have done before and not just, plow ahead. We want to use things that people figured out already. Okay, so when you see, how many of you have a scientific calculator? Okay, good. If you have a scientific calculator, you probably have C and R on there. You probably also have PNR. Yes? Or no? How many people have that? Okay, so if you have a P on your calculator, it is permutations without replacement. So permutations with replacement, they are so easy. That's why you don't have a button on your calculator, because you have a button on your calculator for n raised to the k. Right? So that's why they don't have that. So they make the buttons for you to do the factorial math. So when we see P, n, k, that's how we write it. It's going to be n factorial over n minus k factorial. Again, that's because I draw k blanks. So however many k is. And I start with n in the first blank. The second blank gets n minus 1. The third blank gets n minus 2. And so on all the way down to n minus k plus 1. So there's k of those. And the rest of the factorial has n minus k slots. So that's why we're dividing by n minus k, because we don't actually want them. We're just saying an easy way to get this is, oh, that looks like a factorial if we chop some of it off. How do you chop it off? By dividing by what was left. So the next number here happens to be n minus k. The number after that is n minus k minus 1, and it goes all the way down to 1. And that's why we divide by n minus k factorial, because that's what this number actually is. So when you have CNK in your calculator, it's going to be equal to PNK divided by PKK. So it's PNK because I actually choose K things in order. And then I divide by the way of reordering K things. So just think of that as if I choose A, B, and C, but I don't actually care what order they were, then I have all these different ways that I could have actually pulled them out, and they all got counted. So when I have three things, if I choose those out, but I don't care about the order, I have to divide by 6, and that is 3 factorial. If I had 4 of them, I had to divide by 4 factorial. Okay, now we're going to get some donuts. Not for real. I know. So I'm going to stop recording for a second. Okay. Now, divider problems. So we're going to get some donuts. You know, speaking of getting your hopes up and dashing them. Or vice versa. Let's say we're going to go to get donuts. And they have 6 kind of donuts at the store. And I'm going to get a dozen. Because who in their right mind gets more than 1 dozen unless you have a whole bunch of people? You really shouldn't get a dozen because you're going to get sick if you eat all those. Okay? But let's say we're going to get a dozen donuts. How many ways are there to get a dozen donuts? Now, I am going to torture you because I'm not going to tell you how. I want you to think about it, and if you think about it for more than 30 minutes, you should stop. Because I'm going to tell you how next time. And I might tell you how on Piazza. Yes? You can have any mixture of the 6 kind of donuts you want. Does this have replacement? Do you care what order they pick your donuts? No. How do you tell? This is the key question. How do you tell if 2 boxes of donuts have different donut compositions? So what you need to do, so this is the challenge problem for you, is not actually to answer this question, which is how do you write down the composition of a donut box so that you know that any 2 ways you write them down will actually definitely be different boxes of donuts? That's your challenge. I'll see you next time.